Hello everyone, we're looking at symmetry today in our unit on transformations. We have in the past covered a variety of transformations like reflections and rotations and translations. And what we're looking at today is really not a kind of transformation in the sense that it is not on a coordinate plane with a rule, the way we did with reflections and rotations, but symmetries does describe a change in the object, so we fit it in this section as well. And we have two types. We have line symmetry and rotational symmetry. The vocabulary is pretty extensive here. I guess I should say the definition is pretty long to describe each of these, so you'll take a moment to jot this down and then we'll have to break it into bits to explain what we're talking about. So, starting off with line symmetry, we describe it as a figure in the plane has line symmetry if the figure can be mapped onto itself by a reflection in a line called the line of symmetry. So when we say a figure in the plane, we're talking about two-dimensional objects, not three-dimensional shapes. So we're saying a two-dimensional figure has line symmetry if the figure can be mapped onto itself. So when we say mapped, we mean that sides line up with sides and vertices line up with vertices. So whether we rotate it or reflect it about this line of symmetry, we're going to end up with a shape that is sort of fitting back into place even though we've moved it in some way. And that line of reflection here is called a line of symmetry. When we were doing our reflections a few days ago, that line of reflection could be on the figure or outside of the figure, so to speak. Here, our line of symmetries are always inside the figure. So we want to determine how many lines of symmetry we can come up with. Here, tracing paper will help to demonstrate with some of the questions we want to take a look at here. If we're looking at a figure like this rectangle, I'm going to start off with a bad example, meaning this is not a line of symmetry. But let's say we have this and we are wondering, can we place a line of symmetry here about its diagonal and reflect over that line of symmetry? And let's see what happens. So I'm going to take my tracing paper and reflect the rectangle over that line of symmetry. So you can we still have that same line of symmetry in the same spot, but you can see that this rectangle does not end up mapped onto itself. We do not have sides lined up with sides and vertices lined up with vertices. So this is not a correct line of symmetry. It is not a line of symmetry at all. If we were to take this rectangle and draw a line of symmetry here, so again, this is another bad example. This is not a correct placement, but let's see what would happen if that was the case. So that we're going to reflect over this line of symmetry, and I'm estimating it to be about that far away from the left-hand side. Then that means we would end up with a figure that looks like this. It would look like this, rather. And so you can see it does not map onto itself. We don't have sides lining up with sides and vertices lining up with certain vertices. So a correct line of symmetry should be more in its middle, passing through its center. And so if we were to reflect this rectangle over a center line, then we would see that it does map onto itself. Sides map with sides and vertices map with vertices. So I'll just draw these in a different color. Here we have a vertical as well as a horizontal line of symmetry. So the question is, how many lines of symmetry does it have? 2. Here we have a pentagon, so we have 1, 2, 3, 4, 5 sides and 5 vertices. So again, just a quick demonstration with the tracing paper. If you can see that this is drawn so that we can draw a line of symmetry right down the center and then reflect the figure over that, we are going to map it right onto itself. And that's exactly what we're doing here. So we have a vertical line of symmetry. To see the others, it might help to just rotate the paper. If you just turn the paper so that you have another side of that pentagon on the base, well, I don't know if it's drawn perfectly, but the intention is we're trying to create a line of symmetry again as if it were vertically positioned because we rotated the paper around so that we could again flip this right side over to the left side and map onto itself. We could keep rotating the paper if that helps you to visualize where these line of symmetry goes. Here's my horizontal base. Here's a line of symmetry through that vertex on the top. And again, the idea is we're taking this right side and flipping it over the left side. Here's another rotation of the paper. So here's another side as the base, and here's the vertex on the top. So again, here's another line of symmetry. And one final rotation. Here is the last base. Here's the vertex on the top. And when we count those up, we should have a grand total of 5. Here's another pentagon, but it's stretched out more sideways and it has a wider width. So we do have a line of symmetry that goes like this, but do we have any of these slanted line of symmetries? Could we put one here, for example? And the answer is no. If you saw that, you are exactly right. We cannot do that. So here's the tracing paper just to confirm that. Here is our pentagon, and we're wondering, can I put a line of symmetry like this at a slant? So we're going to reflect it over, and let's see what happens. No. All of the sides and all of the vertices do not map. So that does not work out. So in this case, we just have one. It's quite possible that you could have no line of symmetries, and that's what we see with this triangle. There are none. No matter how you draw a line, you cannot reflect it over that line of reflection to create a mapping. Here we have a trapezoid, and we have one line of symmetry in this case. This is essentially a square. It's just been rotated, and so we have lines of symmetry that go through the sides, as well as lines of symmetry that go through the vertices. So grand total of 4. Here with the tick marks on our triangle, this is an equilateral triangle. All the sides are equal in length, and so that means that no matter which way we rotate our paper, we will have the exact same triangle every single time, meaning that we can draw a line of symmetry through a vertex and its opposite side, much like we could with this regular hexagon. So no matter how we rotate this triangle, we're returning to the same situation where we could draw a line of symmetry through a vertex and its opposite side, and you get that mapping effect where the left side would reflect onto the right side and create 2 symmetrical halves. So that means we have a grand total of 3 lines of symmetry. So some of your book problems will simply ask find or identify the lines of symmetry. Other problems will say talk about the rotational symmetry, and that's where we're going next here. But to calculate the rotational symmetry, we need the lines of symmetry. So that was a first crucial step. Now we're ready to talk about the next topic. Again, we have a really long definition here as we talk about a rotational symmetry. So once again, a figure in the plane is describing a 2-dimensional figure, so no 3D shapes here. A 2-dimensional shape has rotational symmetry if the figure can be mapped onto itself by a rotation of, and there's 2 criteria, 180 degrees or less. That's the first. And the second criteria is that we have to rotate about the center of the figure. So we have to figure out how to find the center of the figure, and then we have to determine how many degrees of rotation will it take to map onto itself. And that rotation must be 180 degrees or less. Alright, so we'll start off with the square here. And again, I'm going to use some tracing paper to help demonstrate a couple of these features. So if we take our square and we were to try and rotate, say, around the side, for example, you would see that it would not map onto itself. All right, so that's a bad center rotation. No, we want to rotate about the center of the figure. So how we find the center is we're going to draw diagonals, and where those diagonals intersect, that's the center. So that's our point of rotation, and that's kind of the second figure you see below it. Alright, so here is my square, and I'm going to now rotate about the center, and we want to rotate it, and if I rotate it like this, you see it's not mapped onto itself. I haven't gone far enough, and if I keep rotating it, now it does map onto itself. Sides map with sides and vertices map with vertices. So the question is, how many degrees of rotation is that? Well, that was a quarter turn. That was 90 degrees. And we could go another 90 degrees. So that's 180 total. And even though we could keep rotating in 90-degree increments, so that would be 3/4 of a turn, that'd be 270 degrees. And now this is my fourth turn, that would be 360 degrees. Even though we could keep rotating it 90 degrees at a time, we just go up to 180 degrees and then we stop. We don't go past that much. So that's why in the second diagram you see drawn just this first turn, meaning that was a 90-degree rotation, and then if we rotate it 90 degrees again, that's equivalent to 180 degrees, and then we stop. We don't go any farther. All right? So the square has rotational symmetry. The center of the square is the intersection of the diagonals. Rotations of 90 degrees or 180 degrees about the center map the square onto itself. Now, one other vocabulary that comes up in your book is this idea of point symmetry. We don't use it very often, and I'll throw it in here as well. So point symmetry is a rotational symmetry of exactly 180 degrees. So if we do have rotational symmetry and we find that it does have a rotation of 180 degrees, then yes, it has rotational symmetry, but we could also go a step farther and it has a special kind of rotation called a point symmetry. That's not too common, and like I said, you only encounter that in a couple of your book problems when they ask, does it have point symmetry? So we would say, yes, this square has point symmetry as well as rotational symmetry. Let's take a look at our hexagon. Here, this regular hexagon means that all the sides are the same length, all the angles inside are the same size, the same measure. Once again, notice that they have drawn the diagonals here, and where the diagonals intersect, that's the point of intersection. So that's the point about which we are rotating. And so if I use my tracing paper to outline my hexagon, and here's my point of rotation, and I rotate this, you can see at which point the sides map with the sides and the vertices map up with the vertices, but how many degrees is that? That's the question. How many degrees of rotation is that? So we need a way to calculate that for shapes that are a little less common. And so here's our formula that we're going to be using. To calculate the rotation, we are going to take 360 degrees and divide it by the number of lines of symmetry. So there's our little formula, just kind of fitting it into the space that we have right there. To calculate the rotational symmetry, we'll take 360 degrees and divide it by the number of lines of symmetry. So the question is, how many lines of symmetry do we see here in our hexagon? We have 1, right, because you can reflect it right side over left side. So from side to side, so that's 1, 2, 3, but then we can also go from vertex to opposite vertex. So there's a 4th, there's a 5th, and there's a 6th. So what that means is our rotation will be 360 degrees divided by 6 lines of symmetry, and that gives us 60 degrees. So each of these little turns are 60 degrees apiece. So yes, the regular hexagon has rotational symmetry. Again, the center is the intersection of the diagonals, and rotations of 60 degrees. And then we're going to rotate it another 60, so that's a grand total of 120. And then we're going to rotate it another 60 degrees, so that's a grand total of 180. So you keep going until you hit 180 and then you stop. So this has 3 rotational symmetries. It also has point symmetry because we do have a measure of exactly 180 degrees. Here's a kite. These two sides are the same length, but they are different in length than these two sides, and these two sides are the same length to each other. And so we have one line of symmetry. So we want to know, does it have any rotational symmetry? So we go 360 degrees divided by the number of lines of symmetry, and we get 360. Well, that's too big. We can only go up to 180 degrees, and we don't go over. So we would say this has no rotational symmetry. Because there is no rotation of 180 degrees or less that maps the kite onto itself. Alright, let's take a look at some other examples with other shapes on the next page. Here in example 3, we have a whole bunch of shapes. We're going to determine, does the figure have rotational symmetry? If so, describe any rotations that map the figure onto itself. That's what we were just doing with our square and hexagon and kite. In fact, these first 3 shapes, the square, the hexagon, and kite, happen to be repeated, so we'll just kind of jot down the results. Line of symmetry equals 4. The rotation is 90 degrees and 180. Here, the hexagon, we saw that the line of symmetry was 6, and the rotations were 60 degrees, 120, and 180. Here with the kite, we saw that the line of symmetry was just 1, and it had no rotational symmetry. Okay, so now for some of these other shapes. So let's take a look at this star. We have this 4-pointed star. We want to first of all determine the number of lines of symmetry. So let's see what we could do. We can draw this vertical line of symmetry, this horizontal, and then we could even draw these diagonal lines of symmetry. So it looks like we have 4 total. So then for our rotational symmetry, we're going to go 360 degrees divided by 4, and that gives us 90. So every 90 degrees will get a rotational symmetry. So that means you have to keep adding 90 onto itself until you hit 180, and then you stop. So that means we have 90 degrees plus another 90 is 180. So it's these two, 90 and 180. That describes the rotations. Alright, here we have sort of a big plus sign. Here's a line of symmetry. Here's a line of symmetry. Here's a line of symmetry. Here's another one. Looks like we have exactly 4. So line of symmetry equals 4. So my rotations, again, we'll go 360 degrees divided by 4, and that turns out to be 90. So every 90 degrees we have another rotation until we get up to 180. So that means we have 90, and then we have 180. It's those two. So you can see that these two shapes really have the same quality of rotational symmetry and line symmetry. They have exactly 4 lines of symmetry, and that means they have the exact same rotational symmetry as well, both 90 and 180. Here in this triangle we have one line of symmetry, and that means we have no rotational symmetry. Here with this heart, again we have one line of symmetry. So now you can see a pattern with these three shapes. The kite, and let me draw that line of symmetry for visual aid. The kite, this triangle, this heart, they're all in the same boat. They all have one line of symmetry, which means they have no rotational symmetry. Last we have this arrow, and it looks like we can draw both horizontal and vertical. So we have exactly two lines of symmetry. So my rotational symmetry will be 360 divided by the number of lines of symmetry. In this case it's exactly 180. So it has two lines of symmetry and 180 degrees of rotational symmetry. So here's a little space for the point symmetry, which we had already described on page 1. Here it is for reference. Point symmetry has a rotational symmetry of 180 degrees. So we could take a look at these shapes we just did, and if any of them came out as 180 degrees, then we can say that in addition to the rotational symmetries, it also has what we call point symmetry. So these qualify, that star qualifies, because we see, the square qualifies, we see the 180 shows up. The hexagon also qualifies, right? All those shapes have the 180 degrees. Here we just have a greater variety of shapes. Again, same idea, identify the line of symmetry and the rotational symmetry. I would have you try this in class, right? You could take a look to see what we did. Here we have two line of symmetries. So my rotation is 180 degrees. The starburst pattern. This one is quite complicated because you have to trace very carefully and count very carefully all of the lines of symmetries that you can possibly come up with. We have this situation where these outer vertices can connect to these outer vertices, but then these inside points, these inside vertices can also connect as well. So here's a 5th, 6th, 7th, and 8th line of symmetry. Yeah, so there's quite a bit here. So line of symmetry is 8 altogether. So for my rotation, to calculate that, we go 360 degrees divided by 8, and that gives me an answer of 45 degrees. But again, we don't stop there with 45. We then add 45 onto itself. We keep adding 45 until we hit 180, and then we stop. So 45 plus 45 is 90. Add another 45 and we get 135 degrees. Add another 45 and we get 180. So you can see this has 4 rotational symmetries. 8 lines of symmetry and 4 rotational symmetries. Here this butterfly figure has a single line of symmetry, and so its pattern is actually behaving very similar to the heart shape and the triangle shape that we saw above, where if you just have one line of symmetry, then you have no rotational symmetries. The football has 2 lines of symmetry. So our rotation is exactly 180. So we have kind of been discussing already which of these figures from example 3 and 4 behave the same rotationally. So here's just one more comparison. If you take a look at the football and this double-sided arrow, You can see they behave the same rotationally because they have the same lines of symmetry, so they have the same rotational symmetry as well. In example 5, again, we would be doing this in class more as a so try it on your own and let's see what we come up with as we're trying to draw these figures. And this is more of a guess and check. Now, could you draw a triangle with exactly 2 lines of symmetry? You might just draw one and see if it works, and if it doesn't work, you scratch it out and you try it again. Or can you draw a regular hexagon with no rotational symmetry? Again, you might try it and see if it's possible. So let's take a look at these two. If we think about a triangle, we could draw a triangle that's very sort of tall and thin, and that would have 1 line of symmetry. And if I tried to make this triangle a little wider at the base so that we had 3 congruent sides, well, then that means we would have 3 lines of symmetry. So I've got 1 and 3, but to get 2 lines of symmetry, turns out that's just not possible. A regular hexagon. Well, we've already seen a regular hexagon. A regular hexagon is what we did on the first page under example 2. Here's a regular hexagon. Remember, a regular hexagon has all the sides being exactly the same size and all the angles being the same measure. And that means if it's a regular hexagon, we're going to come up with 6 lines of symmetry. And so can we draw it with no rotational symmetry at all? No, again, that's not possible. Because if it's regular, it has 6 lines of symmetry. And if it has 6 lines of symmetry, then that means it does have rotational symmetry of 60 degrees, 120 and 180. So to have no rotational symmetry, it would have to be some other kind of crazy shape. 1, 2, 3, 4, 5, 6. There's a hexagon, but it's not a regular hexagon. So again, this is just not possible. A trapezoid with exactly 1 line of symmetry. We saw something like that again on page 1. There it is. There's your trapezoid with a single line of symmetry. We would call that an isosceles trapezoid. Doesn't matter if the big base is on the top or the bottom, but you want your left and right sides to be the same length, and there's your 1 line of symmetry. Can we draw a quadrilateral with exactly 2 lines of symmetry? Well, again, if you think of a square on page 1, this is a square. It was just sort of positioned on its vertex. This is a square with, it's a quadrilateral with 4 lines of symmetry. And here's a quadrilateral with exactly 2 lines of symmetry. So to draw a quadrilateral with exactly 2 lines of symmetry, we don't want to draw a square. We want to draw a rectangle instead. And with that, we finish up our notes.